So in this video, we're going to discuss the properties of the cross product. So we're going to start with the algebraic properties of the cross product. And so we're going to assume that U, V, and W, these are all vectors in space, and C is a scalar. So some of these we saw in our last video. So the first one is that if I take U cross V and I compare it to V cross U, they're not equal. They have opposite signs. So there's a minus out there in front. If I take U cross a summation of two vectors, you can distribute. So it's U cross V plus U cross W. If I take a scalar multiple of a cross product, I can distribute that scalar either to U, or I could distribute it to V. If you take the cross product of a vector with the zero vector, you get the same thing as you only get the zero vector, and it doesn't matter which order you take that cross product in, you always get the zero vector. If I take the cross product of a vector with itself, I get the zero vector, which we saw last time. And then finally, if I take the dot product of a cross product, it's the same thing as if I switch the operations. If I take cross product and then a dot product. Okay, so those are the algebraic properties. Now let's talk about the geometric properties. So let's say I have two vectors, U and V. They need to be non-zero vectors in space. And I'm going to take theta is the angle between U and V. And here are some important properties. So the first one is that the cross product is orthogonal to both the vector U and the vector V. So the cross product is orthogonal. Remember, that's the same thing as perpendicular. So the cross product is perpendicular to U, but it's also perpendicular to V. The second property is that if I take the magnitude of the cross product, it's the magnitude of U and times the magnitude of V times sine of theta. And again, theta is the angle between U and V. The third property is that if I take the cross product of U and V and get zero, the only way that happens, if and only if, U and V are scalar multiples of each other. So that's a way of telling that they're parallel. Remember, parallel vectors are scalar multiples of each other. And the very final property, which we are going to use in a little bit, is that U cross V, this magnitude here of this vector, it's the area of a parallelogram having U and V as adjacent sides.